Hey, my name's Ted Sargent. I'm at Northwestern University, and I'm here to update on progress in perovskite solar cells with a special focus on the inverted architecture. So I'm going to start off with kind of an overall view of where the field has come, looking mostly at performance and stability, but then I'll dive into some of our own group's contributions from 2023, starting with single junction devices, looking at both the interfaces first, the bottom one between the HTL and the active material, and then the top one between the ETL and the active material. And I'll finish with some tandems and some triple junctions. So looking overall, single junctions, interestingly, are reaching substantial parity between the normal devices, the NIPs with the HTL on top, and the PINs, which used to be a bit behind but have since come up. So PINs, as I said, also known as the inverted device with the HTL, typically an inorganic HTL on the bottom. And good progress to keep up with these small area devices, to keep up as we scale. So an initial 1 square centimeter coming fairly close as well in terms of performance. And then, of course, the story of the tandems is incredibly exciting. The perovskite silicon, the perovskite, and also with other active materials. So I'm really presenting on behalf of a whole group today, and you'll also see many of the talks by these members at the Boston MRS 2023. I've highlighted in yellow the folks that are giving talks this week, and I'll also call them out specifically throughout my presentation. That's how I use yellow highlighting. So for here, for example, when we summarize progress in the PIN device efficiencies and the fact that it has by just a mile margin overtaken the NIP for the first time, I'll note that many of the contributions are being discussed in greater detail at the Boston MRS, such as this talk by Dr. Hao Chen on Wednesday, and talks by Dr. Chung Liu, Dr. Soman Park ×2, based on a number of different approaches that I'll describe today. You'll see also that we try to emphasize in this talk, and also especially in the kind of headline numbers for our papers, we try to emphasize the QSS certified, so the quasi-steady state, just to not get sort of caught up in discussions about whether hysteresis is playing a role. We sit at a stable illumination intensity and at the maximum power point and report the power conversion efficiency under those conditions. You'll also see some talks relating to interface engineering of perovskites, scaling on perovskite modules by Dr. Yi Yang, and a talk by doctoral student Aidan Maxwell about some underlying material science for perovskite tandems, and also similarly by Dr. Chongwen Li. So obviously performance is important and stability is just as important. And so this is an area that's also been seeing a lot of focus and a lot of progress. I'll be making reference to various ISOs protocols and standards today, including the dark storage and also under illumination. I think it's fair to say that maybe my favorite is the ISO cell 3, which is being reported at the maximum power point and at 50% relative humidity, and typically at either 65 or 85 degrees C. You'll see that temperature called out. So importantly, this high performance united with high stability is getting a very large amount of attention. And so you'll see here kind of a summary of progress on the PCE at temperature. When I say at temperature, I mean these PCEs, which are a little lower than some of the headline numbers, they're a little lower because instead of operating near room temperature, these are actually operating at 85 or 65 degrees C. And you'll see a lot of interesting numbers here, like exciting numbers in terms of operating lifetime in the 1 to 2,000 hour range. And the idea is to kind of unite that with best available PCEs, which has been the focus of the field. So as I promised, I'll dive into some of the specific advances, and obviously I'll focus on some of the contributions made by our group in the last year. One critical interface is the buried interface in the inverted devices. So this corresponds to the HTL perovskite interface. So here nickel oxide is widely used, but there are challenges. One is the potential for delamination. Another is reactions that can occur at this interface. So in terms of our efforts, Dr. Chong-Wen Lee, who you'll get to meet in person this Thursday and give a little more detail on some of his projects, was really interested to see whether we could develop molecular layers to kind of bind together the inorganic HTL with the active layer. And after screening a number of candidate Lewis-based functional groups, Chong-Wen found that diphosphenes had the potential to provide good defect passivation, but actually form a bridge between the underlying inorganic HTL and the overlying perovskite layer. He saw evidence of increased mechanical strength resulting from improving the control over this interface. You see on the right that when Chong-Wen and his colleagues developed a test for delamination, found a higher load at break when they did the DPP treatment. I'll just emphasize that the final author on this is Professor Yanfa Yan at University of Toledo. Chong-Wen did the bulk of the origination of this work while he was working with Yanfa, and then he continued and completed the project in our group. So some of the indicators that this is effective, one is hyperspectral PL with and without DPP, where we see evidence of a better spatial distribution of the photoluminescence, and particularly so after illumination. You'll see both a narrower post-illumination distribution of brightness in PL, and you'll also see it rise to a higher value compared to some of the loss that you see in the absence of the DPPP. So this correlated with interesting device performance. I think I'll highlight in particular the power conversion efficiency after aging under open circuit conditions in this case, but at quite a high temperature of 85 degrees C. And you'll see devices here that sustained about 1,500 hours of impressive performance. Still focusing on the buried interface, I'd like to talk about another strategy. And this one's based more on self-assembled monolayers, and in particular starts from the recognition that the carbazole-based SAMs like 2-PAC-C and 4-PAC-C are seeing a lot of attention and contributing to a lot of progress in performance. And so in the work I want to talk about now, led by Dr. Soman Park, who's giving a talk on this on Tuesday, the topic that Soman and her colleagues focused in on particular was the question of whether we could integrate good perovskite active layers with textured FTO. The idea of texturing, of course, is to increase the photocurrent with the aid of light management. Now, the specific challenge that Soman and her collaborators faced was to implement the desired 2-PAC-C whole selective contact, but to coat it successfully and substantially uniformly onto this structured substrate, or this textured substrate. And we found evidence initially using molecular dynamics that one of the things that can happen is that these passivation molecules can actually agglomerate. They can make dimers, trimers, and tetramers. We saw mostly dimers, but a few of the higher order ones as well. And our idea was that this could potentially lead to local clusters rather than the desired uniform coating. In further MD studies, when we contemplated the addition of a new component, 3-MPA, in combination with the phosphonic acid, we found a trend wherein it appeared that we could reduce the concentration of the clusters, or reduce the propensity to form clusters. You can see this in the top view over here. You can see the clustering on the left in the control case with just the phosphonic acid, and the improved uniformity projected in MD with the mixture. Experimentally, we saw quite a bit of evidence that these benefits were being accrued. So from Kelvin probe, we see a better spatial uniformity for the mixture of molecules compared to the control case. From wettability or wetting angle, you'll see that we see a higher degree of hydrophobicity when we use the mixed SAMs. And then we did a microscopy study to try to look at the gap between the underlying FTO and a layer that we put on kind of artificially, this was moly oxide, to provide for contrast and therefore to provide for the ability to estimate the effective thickness of the monolayer. And the most striking thing was that there were times in the absence of the new SAM technology where the gap fell below a nanometer. But when we used the mixed SAM approach, the gap was always greater than a nanometer and typically in the 1 to 2 nanometer range. So in terms of device performance, this enabled us to report a 24.8 QSS certified PCE, and to do it on devices that also exhibited interesting stability. And so you'll see on the bottom right here, the MPP tracking time going up to 1,000 hours for these devices operating at 65 degrees C and 50% relative humidity, and retaining 95% of their peak PCE at that operating temperature over the course of that 1,000-hour period. I'd now like to turn to the top interface of the single junction devices and emphasize that clearly this is another crucial physical interface and chemical interface that we need to pay significant attention to. And that in particular, as we continue to rely on the C60 on top, we need to pay attention to quenching effects that originate when it's applied and to explore molecular strategies at these interfaces that can reduce the quenching that occurs when the C60 is put on. So this is a very recent report, just came out from Dr. Cheng Liu, also something that Cheng is going to talk about in person this Thursday at MRS. It's a study that looked at how there may be limitations if you only implement a single molecular strategy based on one class of molecules, because you really have two things that you need to address. The first is surface recombination contributed at surfaces by the presence of defects. And the second is just the natural interface recombination that could occur even without defects, but it occurs because of a reasonable high accumulation of electrons that can meet up with holes in the active layer. And so Cheng in this work sought a strategy that could unite field effect passivation to keep the holes away from the interface, and then also a chemical passivant to deal with the passivation of the chemical sites. So he began by screening a number of candidate diammonium and ammonium ligands, and you'll see some interesting trends here on the right. Of course, we already know that the diammoniums like the EDA and the PDA do increase the PCE of systems, in this case by about 1 power point in this study. He then added a chemical passivation with BA and AA. But then he started to look at the methyl thioammonium ligands as a means to tune dipole moment and got some pretty interesting results. You'll see here through these mixed strategies, combining a diammonium and the methyl thioammonium, a notable increase in the power conversion efficiency. So this is something that Cheng and his colleagues studied in further detail. One strategy was to use a dual spray inking approach to look at the various combinations, the best based on the 3M TPAI, and a less good system based on AAI. And using SIMS, we were able to look at the ratio of these components, finding a higher presence, and we think therefore a stronger binding for the 3M TPAI. And on the right-hand side, a PL intensity distribution for the same sample, looking at how PL is significantly enhanced through the combination of the optimally chosen bimolecular strategy. The concentration dependence is also quite interesting as a function of whether you take a single molecule class or whether you look at the combination of molecules. We can see that if we use PDA-I2 alone, we don't get the enhanced PL quantum yield before putting the C60 on, but we preserve what PL quantum yield we have when we do put the C60 on. So this is suggestive of the field effect passivation role. And then in the case of the 3M TPAI, before the addition of the C60, we do get the increase in PL with concentration, but then if all we have is the 3M TPAI, we do lose the PL when we add the C60. And then the most interesting result is that when we use the dual passivation strategy, which is labeled DMDP in all of these figures, we do improve the photoluminescence quantum yield before we add C60, and we retain it after we add C60. And correspondingly, we get an interesting improvement in the power conversion efficiency, suggesting that we really have combined passivation with decreased carrier recombination. In terms of devices, this enabled a QSS certified PCE of 25.1%, a stable operation over 2,000 hours at 65 degrees C in the ISIS L3. And it also enabled us to report some interesting all-perovskite tandems a little bit above 28%. Another area now still focusing on the top interface is in really striving to drive up the temperature at which devices can perform and can continue to perform well. And I see this as really fitting into the field of accelerated aging, where Lynn Liu and her colleagues have done such important work in being able to sort of provide projections for realistic operating times by virtue of being able to go to much higher temperatures and provide Arrhenius plots to project operating lifetimes. And so our interest in this area, it's something that Soman will also talk about in a separate talk on Tuesday of this week, has been to look at the origins of thermal stability, or rather the limitations of thermal stability in some of the 2D, 3D heterostructures. Many of these rely on phenethyl ammonium, PEA. And one of the things you can see in transient reflection spectroscopy is the following aging, the emergence of a lead iodide related phases, the product of the degradation of the 2D phases that are forming the heterostructure in the as-created devices. So Soman, in this recent report, studied, initially using angle-resolved X-ray spectroscopy, the penetration of various candidate ligands beneath the surface of the perovskite. So some PEA, as our canonical example, will invade and will form the 2D layer on top, some 10 or 20 or 50 nanometers in. And others, and Soman particularly found the anilinium and fluorinated aniliniums were able to limit the ligand penetration and substantially form a surface layer only. And so this is something that, as I mentioned, we can look at with combination of transient reflectance, and we can complement it with GWAX. So when we look at the PEA, we see in the transient reflectance the evidence of the 2D phases. We see no evidence of that when we work with either of the two aniliniums. When we work with GWAX, we can see evidence of lead iodide forming if we just use the regular anilinium, and we can prevent that through the use of the fluorination. With DFT, we gained some support for a physical picture of how this occurs. One finding was that the fluorine substitution produces a higher positive charge density near the ammonium group. And this is something that we believe could enhance binding with the negatively charged MA vacancies. And this then is suggestive of a strong interaction for this best molecule with the perovskite surface. In terms of the device performance, these devices had NREL certified 24.09% efficiencies and exhibited a 1600-hour MPP 85 degrees C tracking time. I'd like to wrap up today by moving from single junctions in the directions of tandems and triple junctions. Here, I'll just highlight a couple of recent works. Many of them you'll see are collaborations with Professor Hairen Tan at Nanjing. And so on the tandems, one of our interesting, most recent points of emphasis in trying to improve tandems has been to deal with the question of passivation in the higher bandgap material, the 1.78 EV wide bandgap perovskites. And here too, the matter of loss of PL quantum yield upon the introduction of the C60 is a crucial issue. And some recent molecular searching has found that, for example, PDA, 1,3-propane diammonium, enabled a very significant reduction in the amount of quenching consistent with reduced interfacial recombination. It also appeared from UPS studies to provide a beneficial upshift correspond to weaker P-type doping, so kind of in the direction of a lightly N-type top surface. This was also reflected in improved spatial homogeneity by doing quasi-Fermi level splitting mapping. We see that the PDA-treated post-C60 surface exhibited indicators of a more promising VOC based on the amplitude and also based on the uniformity of the quasi-Fermi level splitting data. And also suggested that PDA can contribute by removing the impurity phases and eliminating the low-dimensional perovskites. In terms of performance, this led to an exciting VOC of 1.33 volts. Good progress for these single junction devices for the high band gap layer of in terms of the PCE, including an NREL certified 19.3% PCE, something that enabled us to integrate these to form tandems that had a 26.3% NREL certified PCE, something that was retained quite well as we scaled to a square centimeter. Another theme for us has been to pursue triple junction devices. This is a report that I spoke about last year from Dr. Zaiwei Wang and his colleagues, focused on introducing rubidium in order to maintain stability under illumination while increasing the band gap. And in particular, the introduction of the rubidium contributed to reducing the light-induced phase segregation, something we were able to follow by looking at the tail that emerges in reference compositions, but that is avoided when we work with the more stable composition contributed by the rubidium. This led to triple junction devices. You can see here the QE reflecting the contributions from the top, middle, and the bottom cells. At the time, an NREL certified 23% PCE and some initial MPP tracking, although not yet at elevated temperatures. The thing I'd like to highlight now about the triple junctions is a very recent work. This is a partnership with a group of Renee Janssen at TU Eindhoven. It's led by Dr. Junke Wang, a postdoctoral fellow who spent time both in Toronto and also at TU Eindhoven, focused on developing more homogeneous compositions in bromide-rich perovskites, aiming at these high band gaps that are of interest in the triple junction. And what Junke found in particular was reduced trap-mediated recombination at a baried interface, and also improved charge extraction consistent with having rendered a more homogeneous distribution in space of the composition of the active layer material in these devices. Dr. Bin Chen, with us at Northwestern, will be talking on Monday, November 27th, about some of the accomplishments that have been enabled by this strategy. So, for example, JV providing a 25% PCE in lab, a 3.33 volt open circuit voltage, and then NREL certified TJ cells with a somewhat higher, still in the 23s, but high 23s device level performance. So zooming out and looking at some of the directions for the field of perovskites, both single and multi-junctions, I think as we recognize that perovskites have the potential to contribute to multi-terawatt scaling of PV, it also is humbling. It reminds us that we need all of these attributes simultaneously. Of course, low cost, for sure, high efficiency, but really dependable. And by that, I mean bankable. So something where you can really prove to investors and customers and financiers that something is going to be able to survive in the field. And survive means at least 25 years, but that's a moving target as well in the direction of 30 and 35 years. So I think, whenever we make progress in perovskite stability, we also always recognize that we're not done, and it's going to be a continuous improvement process, and that deeply understanding the durability science of perovskites is going to be an ongoing activity for a while to come. And then finally, there isn't really the opportunity to make a trade between efficiency and stability. We need them both simultaneously. So I think studying at every interface will continue to be very important, and this includes, of course, mechanical reliability. This can be influenced by wrinkles and structures. We need to think about the causes of loss of adhesion, the causes of delamination, as one of many possible forms of loss of long-term stability that need to be understood and addressed. Accelerated testing is, again, also very much a kind of long-term activity that's going to continue for a long time. I suspect that as a community, we'll continue to evolve our perspective on what's the right long-term stability, both from an applied perspective, but also thinking about developing models that are predictive and that allow us ultimately to ascertain that we're making cells and modules that will last under outdoor conditions. And this then, of course, corresponds to doing outdoor testing, which I know is a growing and exciting area for the field of perovskites. And it will also involve linking the more controlled scenarios where we can develop physical insights into what actually happens in terms of outdoor failures. So this is obviously a very exciting time for perovskites. We have, as a community, ambitious goals of further increasing the PCE and mastering the operating stability. There's been so much progress, but there's so much more to be made. And key elements definitely include stable materials compositions, and for sure studies of interfaces, ever more demanding accelerated testing and related mechanistic understandings. And with that, I'd like to acknowledge the people that did the work that I spoke about today, and also the people that did some of the work that I didn't speak about today for reasons of time. I'm very fortunate to work with an outstanding team of ambitious and creative and very rigorous and demanding scientists, engineers, and they're shown here. Thank you.